Active Reader, Chapter 1, Section 2, pages 5 through 12. Introduction to Earth Science, Science as a Process. Key Ideas, Chapter 1, Section 2. As you read this section, keep these questions in mind. How is science different from other fields of study? What are scientific methods? How does scientific knowledge change? How does science affect society? Questions to be answered, page 5, chapter 1, section 2. Question number 1, reading check. Explain what are two assumptions that all scientists make. How is science different from other fields of study? Art, architecture, philosophy, and science are all examples of fields of study. However, science has different goals than other fields of study. For example, a philosopher may ask questions such as, why do we exist, or what is the place of humans in the universe? Scientists do not seek to answer questions such as these. Instead, the goal of scientists is to explain natural events. Scientists look for answers about how the natural world works by making observations and by doing experiments. As they study the natural world, scientists assume two things. It is possible to understand nature. Nature is predictable. Highlight those two things. It is possible to understand nature. Nature is predictable. Both of those should be highlighted. They answer question number 1. Question number 1 asks, what are two assumptions that all scientists make? Your answer to that question is, it is possible to understand nature, and nature is predictable. Scientists must first assume that people can understand nature. That is, scientists assume that with the right tools and correct methods, they can find the answers they are looking for. There are many natural events that scientists do not yet understand. Scientists assume that they will someday be able to understand these events. Scientists also assume that nature is predictable. In general, scientists observe patterns in nature. From the way a pattern repeats, scientists can predict that an event will happen in a similar way in the future. For example, suppose a scientist observes that certain weather conditions happen before a tornado forms. The scientist may predict that when these same weather conditions happen again, another tornado will form. Page 6. The questions to be answered on page 6. Why is there an arrow pointing from drawing conclusions to asking questions? On what do scientists base their hypotheses? What are scientific methods? Over time, scientists have developed methods or a set of ways to study the natural world. The methods scientists use are organized and logical. However, these scientific methods are not a set of rules that scientists must follow in an exact order. Instead, scientific methods are guidelines that scientists follow to help them solve scientific problems. The flowchart below shows one way that a scientist may use the scientific methods. Highlight the flowchart by drawing a box around the flowchart. Making observations, asking questions, forming a hypothesis, testing a hypothesis, drawing conclusions, communicating the results. Observing and asking questions. Scientific methods generally begin with observation. Observation is the process of using the 5 senses to collect information about the world. When you compare the colors and texture of two different rocks or listen to waves crashing on a beach, you are making observations. Observations the scientists make often lead them to ask questions. For example, a scientist might observe that the weather is often cooler after a thunderstorm. He may then ask a question: why is the weather cooler after a thunderstorm? Forming a hypothesis. Once scientists have asked a question and made a few observations, they might then form a hypothesis. A hypothesis is a possible way to explain or solve a problem. Scientists base their hypothesis on observations or on known facts about similar events. Highlight that sentence. Again, highlight: scientists base their hypothesis on observations or on known facts about similar events. Write that sentence as your answer to question number 3. On what do scientists base their hypothesis? Scientists base their hypothesis on known facts about similar events. For example, a scientist might know that when hot air and cool air mix, they can form clouds and rain. She could make the hypothesis that thunderstorms happen when cool air moves into an area and mixes with hot air. The mixing air causes the thunderstorm. The weather is cooler after the storm because the cool air has moved into the area. Page 7. Questions to be answered. What are 2 ways scientists can test a hypothesis? What might be the dependent variable in Shannon-Lucid's experiment? Testing the hypothesis. After scientists form a hypothesis, they look for ways to test it in an investigation. In some investigations, the scientists will make more observations and see if they fit the hypothesis. Highlight that sentence. In some investigations, the scientists will make more observations and see if they fit the hypothesis. The first answer to question number 4, what are 2 ways scientists can test a hypothesis? Observation. Write observation on the line. For example, a scientist may use tools to study the movement of cool and warm air. He could use the measurement he takes to learn whether cool air moves into an area after a thunderstorm. In other investigations, a scientist will do an experiment to test a hypothesis. Highlight that sentence. In other investigations, a scientist will do an experiment to test a hypothesis. That is the second answer for question number 4. Write experiment on the line. An experiment is a set of procedures that a scientist carries out. Every experiment has conditions or factors that can change. These factors are called variables. There are 2 types of variables. Highlight the 2 types of variables as I read through them. Independent variables are factors that the scientist changes. Dependent variables are factors that change as a result of the independent variable. For example, suppose a scientist did an experiment to learn how water affects a plant's growth. The independent variable is the amount of water the plant gets. The dependent variable is how much the plant grows. Highlight the sentence, the dependent variable is how much the plant grows. In this experiment, the scientist would change only the amount of water each plant gets. She would keep all other conditions, such as amount of sunlight, temperature, and the type of plant, the same. This astronaut, Shannon Lucid, is observing wheat plants growing in space. Experiments like this one will help scientists learn how plants grow in space where the pull of Earth's gravity is weaker. Question number 5 asks you, what might the dependent variable in Shannon Lucid's experiment be? The dependent variable in Shannon Lucid's experiment would be the amount of growth seen in the plant. Similar to the example given in the reading in the paragraph above, the independent variable in Shannon Lucid's experiment is location. She is either on Earth or in space. The dependent variable is how much growth is seen in the plant. Drawing conclusions. Scientists must decide if their observations support the hypothesis or show that the hypothesis was correct. Highlight as I read the rest of the paragraph. In many cases, the results of an experiment are unexpected. If the results do not support the hypothesis, the scientists must throw out the hypothesis or change it. Unexpected results are important to science. They can cause scientists to ask new questions. Summarize this portion of the paragraph for question number 2 on page 6. A simple summary of that would be, if the results of an experiment do not support a hypothesis, scientists must ask questions and determine why. If the results of an experiment do not support a hypothesis, the scientists must ask questions and determine why. Page 8. Questions to be answered. What is the main reason scientists use models? What are 2 advantages this physical model has over the actual mountain? How do scientists use models? In earth science, it is often impossible to use an experiment to test a hypothesis. Highlight, it is often impossible to use an experiment to test a hypothesis. Answer question 6 at this time. What is the main reason scientists use models? It is sometimes impossible to use an experiment to test a hypothesis. Therefore, scientists use models. It is sometimes impossible to use an experiment to test a hypothesis. Therefore, scientists use models. Instead, scientists make additional observations to gather evidence. Then they test the hypothesis by thinking about how well the hypothesis explains the evidence that they gathered. Scientists also may use models to test hypotheses they cannot test using an experiment. A model is a description or a representation of an object, an idea, a system, or an event. Some models describe objects such as atoms. Others describe processes such as the water cycle. Scientists often use models to study things that are too big, too small, too fast, too slow, or too dangerous to study directly. Highlight that part of the sentence, beginning with study things that are too big, too small, too fast, too slow, or too dangerous to study directly. Types of models. The table below describes 5 types of models that scientists use. Physical, which is a 3-dimensional model. an example, a globe. Graphical, which is a two-dimensional model. Maps or charts are examples. Conceptual, description of an idea. Flowchart would be an example. Mathematical, mathematical equation that describes the way a system or process works. Example, 2 plus 2 equals 4, used to represent two items joined to two other items. Computer, a type of mathematical model that uses a computer to do calculations and display results. Example, computer model of Mount Everest. The scientist is working with a physical model of Mount Everest. The model has the same shape and relative position of the features that the real mountain has. Question number 7 asks, what are two advantages this physical model has over the actual mountain? The first answer would be, you can see the entire set of physical features of the mountain because the mountain is smaller. You can see the entire set of physical features of the mountain because the mountain is smaller. It's also safer to look at features this way because you don't have to climb the mountain. So it is safer as a result. Page 9. Questions to answer. Why is the International System of Units important? If there were another picture labeled poor accuracy and poor precision, what would it look like? How do scientists make accurate measurements? Scientists gather information during investigations. Measurement is a very important method for gathering information in most scientific investigations. SI units. Scientists need to be able to compare and analyze each other's results. Therefore, scientists around the world use a common system of measurement. The system is called the International System of Units, or SI. Meters and kilograms are examples of SI units. Highlight the first sentence. Scientists need to be able to compare and analyze each other's results. Also highlight scientists around the world use a common system of measurements. Question number 8 is answered from those statements. Why is the International System of Units important? Scientists can compare and analyze each other's results using the same measurements. Again, the answer to question number 8. Scientists can compare and analyze each other's results using the same measurements. Accuracy and precision. Accuracy and precision are two ways to describe measurements. Accuracy describes how close a measurement is to the true value. Precision describes how exact a measurement is. Highlight those two definitions. Accuracy describes how close a measurement is to the true value. Precision describes how exact a measurement is. For example, stating the length of a string as 1 meter is less precise than stating the length of the string is 1.05 meters. A measurement can be accurate but not precise. A measurement can also be precise but not accurate. Scientists want to have measurements that are both accurate and precise. The figure below shows the difference between accuracy and precision. The figure at the top left, good overall accuracy but poor precision, meaning that the rings were close to the stake but they were in different locations with different measurements. The diagram at the top right has poor accuracy but good precision, meaning that the measurements were very similar between the distances of the rings and the stake. However, they missed the stake. The diagram at the bottom, good accuracy and good precision, means that the rings not only hit the stake, but their measurement is very similar. No measurement can be completely precise. There are two ways to express error, as a percentage error or as confidence interval. To answer question number 9, if there were another picture labeled poor accuracy and poor precision, what would it look like? The rings would be scattered at a distance from both other rings and would be at a distance from the stake, meaning that they missed the stake and they weren't close to one another. Page number 10, questions to be answered. You have made a meter stick out of cardboard, but you're not sure how accurate it is. You measure your stick against a real meter stick, you find that your meter stick is only 90 centimeters long. What happens during peer review? Percentage error. A percentage error is one way of expressing how far a measured value is from a true value. You can use the following equation to find the percentage error of a measurement. Highlight the equation. The equation is percentage error equals actual value minus measured value divided by actual value times 100. Use the formula to answer question number 10. A meter is 100 centimeters. So your actual value, which will be used in the formula, in the top left and under, will be 100. So you will have 100 on the top left. Your measured value is 90. And you will divide by 100. And you will multiply your answer by 100. (100 minus 90) gives you an answer of 10. Divided by 100 times 100. (10 divided by 100) gives you an answer of 0.1, which you will multiply by 100. Giving your final answer of 10%. You should plug the numbers into the formula, write that equation for question number 10. Your answer final should be 10%. Confidence interval. A confidence interval describes the range of values for a sample of measurements. For example, suppose a scientist wants to express the values for the length of ears of corn in a field. The average length of all ears of corn in the field is 23 centimeters. Of all ears, 90% of them are within 3 centimeters of this average length. The scientists may report the average length of all of the ears of corn in the field as 23, the average, plus or minus 3 centimeters, with 90% confidence, because 90% of the ears of corn were within 3 centimeters of the 23 centimeters that was measured. How does scientific knowledge grow? When scientists discover something new, they share their ideas with other scientists. The other scientists review and test the ideas before accepting new ideas. Sharing results. Scientists typically share their results as papers in scientific journals. They also share ideas at meetings with other scientists. Many journals are now published online, so scientists can share their ideas more quickly and easily. Peer review. Highlight the first paragraph. Before scientists publish their work, they show it to other scientists who are experts on the topic. Those experts review the work. The reviewers may suggest changes to the investigation. They may also point out errors in thinking that scientists did not see. This process is called peer review. If reviewers think that the ideas are incorrect or that the investigation was invalid or flawed, the journal will not publish the paper. The peer review process helps, highlight the next portion of this sentence, make sure only well-supported ideas are published. Again, highlight, make sure only well-supported ideas are published. Your answer to question number 11, what happens during peer review? Scientists show their work to other scientists who review it. Scientists show their work to other scientists who review it. Reviewers may ask for changes or point out errors in their work. Page 11, questions to be answered. What is the relationship between a hypothesis and a theory? Suppose scientists find evidence of dinosaur fossils that are only 30 million years old. What effect would this new evidence have on the hypothesis that the figure describes? Developing a theory. After a scientist publishes his ideas and results, other scientists typically test the hypothesis and build on the results. The process of repeated testing may continue for years. In time, the hypothesis may be proved incorrect, be changed, or be accepted by most scientists. When a hypothesis has been tested many times and becomes accepted, the hypothesis may help form a theory. Highlight that sentence. Again, highlight, when a hypothesis has been tested many times and becomes accepted, the hypothesis may help form a theory. That is also your answer to question number 12. Question number 12 is, what is the relationship between a hypothesis and a theory? Hypothesis that has been tested many times and proven correct may help form a theory. A hypothesis that has been tested many times and proven correct may help form a theory. A theory is an explanation that is supported by all existing observations and study results. However, if repeated results from later tests do not support the theory, scientists may need to change it. The importance of interdisciplinary science. Scientists from many different fields of science share their ideas. Sharing ideas between fields is important because discoveries in different fields may add support to one idea. When an idea is supported by evidence from more than one field, the idea is more likely to be accurate. The figure below shows one hypothesis that is based on evidence from several fields of science. Paleontology, study of fossils. No dinosaur fossils exist in rock layers that are less than 65 million years old. Geology. Scientists found a large impact crater in the ocean that is about 65 million years old. Astronomy. All over Earth, iridium appears in rocks that are about 65 million years old. Iridium is rare on Earth, but is common in asteroids. Climatology. Scientists have used computer models to show what would happen if a large asteroid hit Earth. They have found that it would change Earth's climate and affect life on Earth. Impact hypothesis of extinction of the dinosaurs. Discoveries and ideas from different fields of science have helped scientists develop a hypothesis about how dinosaurs became extinct. This should help you answer question 13. Suppose scientists find evidence of dinosaur fossils that are only 30 million years old. What effect would this new evidence have on the hypothesis that the figure describes? The hypothesis would be found to be incomplete or incorrect. The hypothesis would be found to be incorrect in estimates of 65 million years. It would have to be thrown out and new questions would need to be asked. Again, the hypothesis would be incorrect, have to be thrown out, and new questions would be asked. Scientific knowledge helps people understand the natural world. It also helps people develop new technologies such as tools, materials, and processes. Many technologies are helpful, but some new technologies can cause problems. For example, plastic is a technology that is useful in many products. However, plastics can cause pollution and harm wildlife. An understanding of science is important for all citizens. Thinking scientifically can help people make wise decisions about products they buy, where they live, and even how they vote. Section 2, review. Questions to be answered. What is the relationship between a dependent and independent variable? What are 6 main processes that are part of the scientific methods? What is the difference between accuracy and precision? Why is peer review of a scientific paper important? Give one example of a technology that can be both helpful and harmful. Think of a different example from the one given in the text. Question number 1. Information can be found on page 7. The independent variable is what the experimenter changes. The dependent variable may change because the independent variable has changed. Question number 2. The 6 main processes that are part of the scientific methods: observation, question, form a hypothesis, experiment or test the hypothesis, draw conclusions, and communicate results. Question 3, which can be found on page 9. What is the difference between accuracy and precision? Accuracy is how close a measurement is to an actual value. Precision is how exact the measurement is. Question 4. Answer can be found on page 10. Why is peer review of scientific paper important? Peer review makes sure only well-supported ideas are published. Question 5. Information can be found on page 11. Paper would be an example of a useful technology, but it destroys trees in general, or generates pollution. You could use many other examples: oil, plastics, as were already given as an example, paper, gas, natural gas, different things along those lines. This concludes the information for Chapter 1, Section 2 of the Interactive Reader.